All right, so in this video, I want to be able to prove that the derivative of inverse tangent is 1 over 1 plus x squared. So this should be commonly known already, right? The derivative of inverse tangent of x, I'm going to put this in parentheses because notation, equals 1 over 1 plus x squared. But why is this true? Okay, let's get started. So I already mentioned the strategy before in my literally previous 2 videos. So if you want to check out why we're using this strat, you can go ahead, or where it came from, go ahead and do that. But basically, it's just, let's call the function we're taking the derivative of f of x. Let's call it f of x. And call it, that's inverse tangent of x, right? Now, we don't know how to differentiate inverse tangent. But if we go ahead and take the tangent function on both sides, right? So tangent of the left-hand side, that just gives you tangent of f of x, like that. On our right-hand side, taking the tangent will cancel out the inverse tangent. So that leaves you with whatever's on the inside, which is just the x. Okay, so now, doing that strategy, you now know how to differentiate everything that is in here, right? You know how to differentiate tangent already, you know how to use the chain rule, and you know how to differentiate x. It's just 1. Differentiating both sides. On the left-hand side, remember the derivative of tangent is just secant squared, right? So we have the secant squared, and then the inside stays the same. It's still f of x. By the chain rule, we have this inner function right here. We now have to take the derivative of it. So we just multiply by the derivative of f of x. On the right-hand side, we just have 1. Now, up here, notice that if we had an expression for f prime of x, then that would just be the derivative of inverse tangent. So that's how we're going to figure this out. We're going to isolate f prime of x. To do that, we divide this guy on both sides. So on the left-hand side, you're going to just be left with this f prime of x. On the right-hand side, you're going to have 1 over all of this crap. So you have secant squared of f of x. Nice. So you now have this. Remember what f of x was. F of x is just inverse tangent of x. So you could rewrite this as secant squared of the inverse tangent function. So are we done? Right? Everything's in terms of x again. Well, no, because you can rewrite secant squared in terms of tangent, and then that'll help you cancel out with the inverse tangent that's on the inside. So on the remember that tangent squared plus 1 equals secant squared, right? So we can replace this secant squared with the 1 plus tangent squared, and that's where we got the tangent from, that it's going to cancel with this inverse tangent that's on the inside. So down here, I'm going to put down this 1 first, then we're going to add it with this tangent squared. And then on the inside of the tangent, we're going to have this inverse tangent. Okay, so now we're going to take a look at this right here. Because to some people it may be obvious, to some people it may be not, but this square, what it's really doing is it's just taking this tangent function and squaring the whole thing, right? So we can also rewrite it as just tangent of inverse tangent, and then square the whole thing. The square being on the outside there, and the square being directly applied to the tangent means the same thing. It just means this function is getting squared. So what happens when this occurs, right? Well, the tangent and the arctangent cancel. So you're just left with this x and the square, right? So this whole thing that I have underlined right here is just equal to x squared. So 1 plus x squared in the denominator, because this whole thing just becomes x squared, and you have a 1 on top. So that's where you get the derivative of the arctangent function. And the arccotangent function, the inverse cotangent function, is really similar to the inverse tangent function. And I'm going to also use a similar strat as I have in the previous videos, right, on inverse sine. Let's first write this down. D over dx of inverse cotangent x. And the strategy that I used to differentiate that was the inverse trigonometric cofunction identity. Basically, I showed you in the last video that if you took two inverse cofunctions, so inverse cotangent plus inverse tangent, and then added them up, you would get pi over 2. So this works for inverse sine, inverse cosine, it works for inverse cotangent, inverse tangent, it works for inverse cosecant, inverse secant. And I showed you why in the video where I differentiated inverse sine. So I'm going to just take this for granted right here. What I want to do is write inverse cotangent of x in terms of inverse tangent. So to isolate this, we have inverse cotangent of x equal to pi over 2. And then we're just going to go ahead and subtract inverse tangent on both sides. So on the right-hand side, you have pi over 2 minus inverse tangent of x. Now, we know how to take the derivative of this thing, right? Because we just found out that the inverse tangent of x, the derivative of the inverse tangent of x is equal to 1 over 1 plus x squared, right? So we can go ahead and plug this in to there. We have the derivative operator on the outside, and on the inside, we just have, instead of inverse cotangent, we replace it with pi over 2 minus inverse tangent of x. Nice. Okay, so now we already know how to take the derivative. The derivative of the first term, pi over 2, is just 0, because pi over 2 is constant. So all we have left is this negative inverse tangent. I'm going to put the negative down on the outside, and then we're going to take the derivative of this inverse tangent, which we already knew is 1 over 1 plus x squared. So that's a really easy way to take the derivative of the inverse cofunction of a function that you already know. Just like I did in the last video, and just like I will do for secant, inverse secant and inverse cosecant, right? They're just negatives of each other. Pretty simple.